Okay, and if you could stop your share, we're now going to move on to Marc Michel. Marc is an associate professor of geosciences and the division leader for the nanoscience degree program at Virginia Tech. He's been using synchrotron methods for more than 15 years to study nanomaterials that are of interest for understanding environmental processes and for preserving water and soil quality. The title of Marc's talk is Synchrotron Total Scattering, a method for studying the structures of poorly crystalline geomaterials. And Marc, it looks like we've got a good connection.
Great, thank you, Peter.
Take it away.
Thank you to the organizers for giving me the chance to speak with you all today. It's wonderful to see so many participants in the workshop. So in the time I have today, I want to tell you about this method, total scattering. We've been using it in our group for a good 15 years now to study both natural geomaterials and synthetic analogs of those materials. And so I'm sure many in the room are interested in geomaterials already, but if this is something new to you, geomaterials generally describes the solid phase products of biogeochemical or just geochemical processes. And so I give you here just some examples of the kinds of systems that we're interested in, ranging from acid mine drainage to river sediments, for example, weathering products, and so forth. The reason we and many others are interested in the solids that are forming in these environments is because they oftentimes are nano-sized and they tend to be highly reactive. And so these are components that are really important in controlling element cycling. So these could be how contaminants or nutrients are moving in environmental systems. What is challenging about studying these materials is that the crystallinity and the sizes of the particles that form can range very widely. And so the total scattering method that I'm going to describe to you today is another tool we have available to us to try to overcome these challenges. Because in the end, what we're trying to do is identify structural details of these materials so that we can develop structure, property, behavior type relationships, exactly what material scientists do, for example. And so we'll start with just thinking about the crystalline components of these systems, because that's normally something we encounter. And Joanne did a wonderful job introducing diffraction. So I just want to build on that briefly by saying when we do, for example, a powder X-ray diffraction measurement to try to understand the identities of phases that are present in our samples. If those materials are crystalline, then we rely on their Bragg peaks. So these are the sharp peaks that are in an X-ray diffraction pattern. And the basic method for identifying different phases is using what I often refer to as fingerprinting. So we're just taking the observed pattern and the peak positions and their intensities. So like you see here on the right in the upper plot, just imagine that is what we observe in our data. And then we're comparing those to the intensities of other known structures. And so we can do this manually by just calculating structures that we get from databases, for example. Or we could there's an automated way to do this that uses sort of search match software with databases. But again, what we're doing is just comparing peak positions and intensities, looking for things that match. So in this case, what we have in our observed sample is simply quartz. And so once we know what's in our sample, oftentimes we want to know how much, especially if we have multi-phase samples, how much of each phase is present. And what are their structural details? So there are some standard approaches to doing this. Full profile fitting, for example, using the Rietveld method, allows us to determine things like the absolute abundances of the different phases that are present. For each individual phase, if we have sufficiently good data, we can learn about the structural details like the lattice dimensions, the occupancies of atom sites, and things like strain. And if we're unsure about which phase we actually have, we can test competing structural models to look for the best fit. And this is routinely done for crystalline solids, including samples that it can have a whole number of different phases present simultaneously. And so what you're seeing in the right here is a relatively simple example of just a mixture of what is mostly calcite with a little bit of aragonite present. Now, when we're dealing with nano-sized samples, diffraction is still a very useful method. But there is something that we refer to as a problem, and that is that as the crystallite size decreases, the width of the peaks increases. And so what I'm showing here in the example on the left is for sphalerite or zinc sulfide. The pattern on the top is for crystalline zinc sulfide, actually a natural sample. And you can see that the peaks are very sharp, very intense, and well-defined. And we can index those with their appropriate Miller indices. What's shown in the bottom two patterns are two synthetic zinc sulfide samples where we've controlled the size such that the one in the middle has an average particle size or crystallite size of 8 nanometers, and the one at the bottom is even smaller at around 2.5 nanometers. And so you can see this effect of decreasing particle size or crystallite size on these diffraction patterns where the peaks become very broad. And at some point, when you get down into this really sort of nanoscale regime, what you start to notice is that some of the peaks, especially these weaker ones that may occur as shoulders, start to kind of disappear. They become effectively lost in the noise or kind of combined with other peaks. And that can make phase identification or a detection of minor phases difficult. It can also affect our ability to extract the structural details that we might be interested in. There is a plus side to this. For a sample like this, we can actually use the peak width to calculate what the average crystallite size would be. This typically works only when we have sizes that are relatively monodisperse and less than 200 nanometers, and there are a number of ways we can actually get this information. Now, if we go even further in that direction, where we may be decreasing size, but we're also taking away the structural order, at least the long-range structural order, we get into what are known as amorphous solids. So glassy or amorphous solids, when it comes to diffraction, have no Bragg component. That's because they have no long-range order or periodicity. What their diffraction patterns are characterized by is a weak diffuse scattering component. And so in the example on the right here, you're seeing quartz powder, so crystalline quartz in green compared to silica fume, which is just amorphous silica. And so even though compositionally these are the same, they're SiO2, the lack of long-range order means that silica fume doesn't have the sharp Bragg peaks, okay? And the problem with that is for that silica fume sample, we're not able to describe this using periodic models that are based on a Bravais lattice. So how do we get that structural information? And so what it's important to remember here is even though a material like this doesn't have long range order, they still do have short range order. In other words, both quartz and amorphous silica are both based on a silica tetrahedron, SiO4 tetrahedron. It just has to do with how those tetrahedrons are connected to one another and how the sort of angles and rotations relate to one another. Okay, and again, if we're interested in understanding the properties and behaviors of materials for an amorphous solid, that's important to us. Knowing how the short range structure is put together will help us to do that. So in sum, there are limits to this sort of conventional crystallography. So it's materials, for example, that have long range order but have some aperiodic modifications. So this is where we can't describe a structure simply by a unit cell. Like we just talked about, there are materials that have limited long-range order. So this can be nano-sized materials where literally the physical dimensions of the particles are limiting the ability to have long-range order. We can also have materials that are partially disordered. And so what you're seeing on the right here is a simulation of a 3 nanometer zinc sulfide particle from a study in 2003. And what you're seeing in this simulation is that the core of this sulfide particle looks like sphalerite. It's relatively ordered, but the few atomic layers near the surface have become all distorted and disordered. Okay, so they're structurally different. You can kind of think of this like a core shell particle. And then, of course, there are these materials that have no long-range order, describing amorphous and glassy solids, like in that previous example. But also, we can think of polymers and small clusters and other complexes that may be the building blocks for minerals that we want to know the structures of. Okay, so what is synchrotron total scattering? And I'll introduce the method and what's called pair distribution function analysis, PDF analysis, which comes from this total scattering data. And so we collect these at synchrotrons, at least preferably, and the images that we collect look similar to what you show here, or what you see here, which are from large 2D area detectors. So for a material that has long range order, we see sharp rings, these concentric rings. These are the Bragg features. When we have no long range order, we still see concentric rings, but we see that they're very broad, diffuse, and weak in comparison. So when we collect the data in these 2D images, what we do is convert it to a 1D pattern. So that's what you're seeing in the upper right here. The sample is shown in black. We measure the holder for the sample, which we call the blank, and we can subtract that directly so that we can isolate the scattering from the sample itself. We subtract that background, as I just said. We generate something called the structure factor, which is really just this diffraction data in a slightly different form, where it's scaled as Q space is increasing. You can think of Q space, it's called momentum transfer. It's just another way of expressing reciprocal space. And then the last step that we typically do is a Fourier transform, and that converts this scattering data into real space, where the x-axis is now distance, or r in angstroms, and the vertical axis is what we call this pair distribution function, or sometimes it's referred to as G of r. And before I explain a little bit more about the PDF, just keep in mind with the bottom line here is that this PDF method, or this total scattering method where we generate these PDFs, is giving us structural information. And the key here is, unlike conventional diffraction measurements, there is no requirement of long-range periodicity. We prefer to use synchrotrons to collect these kinds of data. As Joanne talked about, we have this freedom in terms of moving to really high energies and having super, super bright X-ray beams, which are advantageous to this measurement. So the pair distribution function, I said, is a Fourier transform of that scattering data. Just remember that every nonlinear function can be represented as a sum of infinite sine waves. So you're seeing this sort of step function here. We can construct or deconstruct as just being a bunch of different sine waves. And so this Fourier transform is commonly used to break apart, for example, sound waves, if we want to convert that into a frequency spectrum. In the case of scattering data, we can also convert scattering data, so that's the reciprocal space form, to this real space form, where we're looking at the x-axis in terms of distance. And so here's an example of a PDF for goethite. Again, the x-axis is distance in angstroms. The y-axis is this pair distribution function, or probability function. And so what you see is a bunch of sharpish positive peaks here. These peaks correspond with average distances between atom pairs. Okay, and if you're in this sort of first portion of this PDF, roughly less than 3 angstroms, those are distances between atoms that are bonded to one another. Okay. The intensities of these peaks relate to the atomic number, so the sum of the Z of the atom pair, and also their coordination number. So that has to do with the area under the peak. The attenuation you see in the signal with increasing R is related to crystallinity. I'll come back to that in just a moment. So if we have a PDF for a sample, we know, or we think we know what the structure is, we can actually do a standard fitting approach, which is really just a real space Rietveld. We're just taking a unit cell structure and fitting it to our data. And this can be advantageous for these nano-sized sample because it avoids some of the issues we see with complex peak broadening. Okay. And there'll be some references here if you're interested in some of the papers we and others have published using this standard fitting approach. When we do a fit like that, we can actually sort of deconstruct the PDF to generate what are called partial PDFs. So here this is for goethite again. You see the goethite structure on the left. The total PDF that you saw in that previous slide is shown on top here in black. And then what we've done is just based on the model fit, we've calculated how the different pairs of atoms in the structure contribute to that total PDF. So for example, the first peak we see here at 1 is just the average FeO distance. And so we see a strong peak here at about 2 angstroms. But we can understand what the other peaks in the PDF represent. So you can see that the iron-iron pairs between edge and corner sharing bonded pairs of atoms and structures can give you these next two strong pairs of distances. But since the PDF is not element specific, it's just weighted towards the Z, you can see that there are other pairs that are contributing to that total PDF. So there's all kinds of information that we can extract about the arrangements of the atoms. And so we've been using this kind of approach for some in situ kinds of experiments to examine the early stages of mineral formation. So this is an approach we've developed over the last couple of years that uses mixed flow reactors, where we're synthesizing materials inside the reactor, where we're pumping in reagents using a syringe pump. We're then passing that solution as it's exiting the reactor with the newly formed particles through the X-ray beam, and we're using our detector to collect the diffraction data. And so what's shown in the plot here on the right are 5 different experiments where we've just changed the initial calcium to phosphate ratio to see how that affects the structures of the products that form at 5 minutes of reaction time. And so the way we can, again, just like you saw on that previous slide, we can sort of take apart the PDF. We know that this first feature that's labeled A here is the average PO distance in phosphate. The second strong feature labeled B is the average calcium oxygen distance for the calcium ions. And then C and D are actually what we've been interested in. These show the connectivity between the calcium ions and the phosphates. And so there are 2 different geometries that we identified. There's this bidentate geometry and then a monodentate, where the monodentate has a longer calcium to phosphorus distance. Right? And so what we see here is the effective ion ratio changing the type of coordination between calcium and phosphate in these solids that are all amorphous. And so this same kind of approach has been used in a slightly different way. This is work by Mike Xu using differential PDF. So here he took ferrihydrite. And so in this little conceptual diagram, just imagine the ferrihydrite is the orangey core. And he sorbed it with sulfate and was interested in, can we use PDF to understand the complexation or the geometry of complexation of sulfate on the surface. And so in the differential method, what you do is you take your sorbed ferrihydrite or sorbed nanoparticle data, you subtract from it the data of just the substrate, so just the nanoparticle. And what's left behind is this differential pattern. And what that shows you is it gives you this information on surface geometry. So it's very much analogous to an X-apse pattern, where you're seeing the distances between the atoms of that adsorbed complex. And so we've been using this method to quantify the abundances of phases using linear combination fitting. So this is work being done by my student, Ali Namayande, who's presenting at Goldschmidt, if you're interested in checking out his talk. And so what we do here is when we have a mixture of samples, some of which might be nanophase or nano-sized, and we want to know what abundances they're present in, we can basically use linear combination fitting, where we take spectra or patterns of the end members. So here we have pure phases of ferrihydrite, goethite, and hematite, and then we can use LCF to determine the phase fractions in a mixed sample. Okay, and so here's an example of that on the left, where Ali had a mixed sample. It's where he's transforming ferrihydrite in the presence of oxyanions like phosphate. And what LCF gives him are the proportions of the 3 different phases, the initial ferrihydrite that's left and the 2 transformation products, which in this case are hematite and goethite. And what we can do if we do this for samples, many samples over time, is we can actually track the formation of these transformation products, their abundances, and also the disappearance or the transformation of the initial ferrihydrite, and calculate, for example, rate constants. And so the last thing I want to tell you about is that PDF gives you information about the degree of crystallinity of your sample. It has to do with the attenuation of these PDF peaks as a function of increasing R. And so a simple example is if we just compare crystalline or bulk gold to a very monodispersed sample of 2 nanometer gold. And you can see the colors corresponding there. And the obvious difference here is that for the monodispersed 2 nanometer gold, the PDFs signal attenuates very quickly. In fact, when you get beyond 2 nanometers or 20 angstroms, it's just been reduced to statistical noise. And that's because if we have a monodispersed sample like this, we can't have 2 atoms that are separated by a distance bigger than the physical dimensions of the particles. Okay, so in this kind of case, for a nanocrystalline sample, the size we get from PDF should be very close to the actual physical dimensions of the particles. But this can get a little more complicated. If we have materials that have structural disorder, we can get size information, but it can decouple from the physical dimensions of the particles. And so here's just an example of how we've applied this in the past. For ferrihydrite, 6-line ferrihydrite is considered the more crystalline kind. You can see the PDF signal continues out to 5 or 6 nanometers. 2-line is less crystalline. You can see it attenuates by around 2 to 3 nanometers. And then when we looked at natural ferrihydrites, which tend to be very poorly crystalline, you can see they're only about a nanometer or so in size based on that PDF estimate. So PDF modeling can get much more advanced than what I've described here. We've published a few papers in collaboration with Andrew Goodwin at Oxford using reverse Monte Carlo, which is just another kind of approach to understanding what the structural information in those data mean. For RMC, we use large boxes of atoms, typically have 10,000 or so atoms inside, where the RMC code is moving the atoms randomly in order to try to improve the fit between the calculated and observed PDFs. And when we do this, we apply constraints, things like closest approach, so atoms can't get on top of one another, for example, or we can fix coordination numbers in order to try to learn things about the average structures of materials, not the exact structure, but the average structure. Okay, and so the takeaway here is total scattering methods are still being developed, both how we do the experiments and how we analyze our data. So with that, I will say thank you for your attention.
Well, thank you so much for that talk, Mark. We really appreciate your taking time away from your vacation to give that. And the floor is now open for questions. And let's see. I am going to start with Christina Lopanos. The questions with the experiments with the syringe pumps in the reactor with the new precipitates being pumped across the X-ray are all cool. What beamline did you set that up at?
Yeah, thanks, Christina. So beamline 11 IDB, and I want to acknowledge Olaf and Uta for their continuing support for our work there. Is where we do the vast majority of our PDF experiments. It's a dedicated high energy scattering beamline at APS, has a very large area detector and a very versatile platform where you can set up a whole bunch of different types of experiments. So I wish I had a picture to show you quickly, but we've set up some really complicated experiments where we've got multiple syringe pumps, multiple reactors, all right there on the beamline. And in those cases, we actually can run wires or connect to the instruments inside the hutch so that we can control our experiment from outside while we're collecting our data. So if you're interested in that kind of experiment, feel free to contact me, or I encourage you to reach out to Olaf as well.
Okay, there's also a question I skipped from James Green. For the zinc sulfide nanoparticles, on the disordered surface layer, is the stoichiometry of zinc to sulfur maintained, or does zinc or sulfur preferentially desorb?
Yeah, it's a great question. There's a whole series of papers that were published by Ben Gilbert and Jill Banfield and Hengzong Zhang, some of which I think tackle that. I don't know the specifics off the top of my head. And I think one of the things they found that's very interesting is the extent to which the solvent interacted with those surfaces changed the amount of disorder that they were seeing, the sort of thickness of that disordered layer, which I can only assume has some consequences for the stoichiometry as well.
Okay, thanks, Mark. We're right at 12:25. There's another question from Dan Hummer. I'm going to ask you to respond to that just through the chat if you would be willing to do that. So thanks again. And maybe you could stop your share.